Very good. Hello. Let's see. Uh, Last class, we saw that uh, the condition that you preserve the symplectic form yields a whole lot of the um, Hamiltonian formalism that we are so familiar from mechanics. Let's review that very quickly. Here it is. So this is the idea. If you have a symplectic form, an anti-symmetric tensor in this 2n dimensional cotangent bundle, and you impose that the Lie derivative along a certain vector field be zero, in other words, that the flows generated by this vector field are going to preserve the symplectic structure, then what you get are curves, the time derivative of theta and the time derivative of pi, that are given by Hamilton's equations, where the Hamiltonian function is this h tilde. So this is where you get Hamilton's equations from. Now, furthermore, if you take any function on this cotangent bundle and the coordinates are x or theta and pi, theta being coordinates on the base manifold, pi being coordinates on the cotangent spaces, then the time derivative of this function along the directions specified by this vector field h, this is just h bar is just dd tau, same thing, are going to be given by Poisson brackets. And the vector field itself, you see here the basis vectors, basis vector, basis vector. This vector field on the cotangent bundle has these components. This here, the h d pi, is the theta d tau. That's the first component. And this piece here, minus the h d theta, is d pi d tau. Very good. So this is what we did last time. We're getting a formalism coming out of this constraint, the preservation of a symplectic form, that is remarkably close to what we want in order to do physics. Now, this all refers to flows on the cotangent bundle of the embedding space. But we want to deal with normalized probabilities. Equals 1. In other words, we want to deal with the cotangent bundle associated to the simplex of normalized probabilities. So how do we handle that? We handle that through a normalization constraint. So the purpose of this first part of the class for today is to discuss how do we handle this normalization constraint on the larger space Ts plus 1, the cotangent bundle there. So the normalization constraint. This is not something that we normally have to worry about in classical mechanics, because although we have Hamilton's equations and all of that, we never have to normalize coordinates in any way. It is because we're dealing with probabilities that all this new variation on Hamiltonian dynamics comes into the picture. So here we go. We're going to define the constraint. Let the sum of these probabilities be equal to, well, we're gonna call it, give a symbol for it, the normalization of theta. That's it. It's as if we're writing the magnitude of theta, but it refers to this sum. So this is a definition. And we're going to define the constraint. This is a function of coordinates and momenta. In this particular case, this scalar function 1 minus the normalization of theta. Clearly the constraint then is given by n equals to 0. So this is the constraint that we want to impose. Now, why do I go about defining all of this? Well, the definition of this normalization here is just for convenience, notational convenience. But the definition of this n in this particular way is designed so that we can consider situations in which n is not 0, right? In general, this n tilde is not going to vanish. The constraint consists specifically in imposing that it vanish. So what we want here to establish is we want Hamiltonian flows on this cotangent bundle. We want Hamiltonian flows that preserve this condition. In other words, if you start with a normalized probability and you evolve it according to these rules, we want to constrain our H tildes, our possible Hamiltonians, in such a way that if initially you had n equals 0, then n equals 0 is going to be preserved by the evolution. So what this means, therefore, is that the dd tau of n, which is given by the Poisson bracket of n with h, be equal to 0. So you see, this is a condition on the allowed h's that we're going to find acceptable. Furthermore, we can rewrite this, or we can just rewrite this as saying, look, if you want the normalization to be preserved, you might as well just write it in terms of the thetas. So here is one possibility. We can just rewrite this as being theta I equals 0, and we can rewrite this as the sum of the theta I d tau equal to 0, or if we use Hamilton's equations, the theta di is the h the pi equal to 0. So this is one way to write down the constraint, the preservation of the normalization constraint. This is another one. Now, there is another little constraint that we would like to put on the h's, although we won't have a chance to talk about it too much, which is that one of the things we want about these evolutions given by this Hamiltonian function h tilde is that not only they preserve the normalization of probabilities, but they also preserve the fact that probabilities are supposed to be positive. So we also want the fact that the probability, the velocity, has to vanish whenever the thetas are vanished. So if you ever reach the boundary of the simplex, you want the velocity there to be 0 so that you don't exit the simplex. Notice that these are n equations, one for each boundary of the simplex, while this equation here or that equation there are just conservation of probability is one condition. Boundary conditions are many. Very good. So what else do we do with this? So let us write this. Let us write this down in a different way. So what I'm going to do now is figure out, okay, let's go back here. If we have a scalar function, we would like to figure out what is the vector n bar associated to that scalar function. So the n vector, we would like to figure out what flows this scalar function induces. So the vector is going to have components along the various basis vectors with the various components, which are just alpha I. And let's invent a new parameter for these flows. What flows does this vector here induce? We use nu as a parameter. And the rate of change of x's with nu, that's going to be given once again by Poisson brackets. It's always the same formulas that we're using here. So this is what allows us to find the vector components that go with the scalar function. It's exactly the same type of equation that we had down here. You have a vector, dd tau, the vector h. It's associated with the scalar function h tilde through the Poisson bracket. And this is true for any function f, in particular for the coordinates. But now we can go ahead and compute this guy here. So let's compute it. So when we have n 1I, this is going to be the theta 1, the theta I, the nu. Here we're going to write the Poisson brackets. So here we're going to have the theta I, the n, minus the theta I, the n, and now take all the appropriate derivatives with respect to the thetas and pi's. The theta j, the pi j, the pi j, the theta j. Okay, when we look at this, you see that this term here immediately vanishes because the theta d pi is equal to 0, so we don't need to worry about that. And furthermore, here we have a delta ij. But n, the scalar function n, depends only on the thetas, right? Since n depends only on the thetas, this is equal to 0. And so what this is telling us is that the component along the one direction, along the theta direction of this vector is equal to 0. Okay, that's the first part we wanted to do. Now let's do the second components. These are the components along pi. That's by definition what this guy is. This is the theta d nu. And we compute once again the Poisson bracket minus the pi I, the n tilde, and here we put the theta j, the pi j, the pi j, the theta j. Very good. When we do this here, we see that this term vanishes. Well, so that's this one, because n only depends on theta. Here we have a Kronecker delta, pi j, and the n d theta, the n d theta j is equal to, well, n is 1 minus the sum, so it's minus the sum d theta j, and the sum, we can put whatever we want here, really, k. So this is just going to be minus d theta k, d theta j, that's just minus 1. Whatever that guy is, this is minus 1. So n to I is equal to d pi I d nu equals minus 1. Plus 1. So conclusion, the vector that we have, the vector n, let's just write our results. 1I is d theta I d nu equals 0, and n to I d pi I d nu equals 1. So now that we have the vector, we can actually find the integral curves. So the integral curves of n. So basically what we have to do is just integrate this. These equations are going to be equations theta as a function of nu and pi as a function of nu. And the solutions are going to be that theta as a function of nu, let's see, the derivative is 0, so this is going to be constant. This is just going to be given by the initial condition. And pi as a function of nu is just going to be given by the initial condition plus the derivative equals to 1. So we integrate this, it's going to be an initial condition plus nu. So what this is telling us is that the integral curves of this vector, the normalization vector, are such that if you move in such a way that if you move in the cotangent bundle in such a way that the probabilities do not change, then the normalization does not change, obvious. But it's also telling you that the flows induced by this vector are such that you can change the momentum by a constant. The point of this, by a constant, meaning this is constant in the sense that it does not depend on I. All components of the momenta are changed together by the same amount. You may start seeing that this sort of resembles the fact that you can change the phase of a vector in Hilbert space by a constant phase, right? And this does not change the physical state. That's more or less where we're going with all of this. And in fact, what we have here is a global gauge symmetry. What is it that's going on here? The idea here is that we have imposed that the normalization here, we wanted the normalization to be constrained. We wanted the evolution to preserve the normalization. And the way we write this is we write this as a Poisson bracket of n with the evolution, the scalar Hamiltonian that evolves the d tau. Very good. This is what we want. But note also that if n is preserved along H, then H is preserved along N. Why? Because this is exactly the same Poisson bracket, except flipped around, which is only a minus sign. So what this means is that if N is preserved along the H evolution, then H is preserved along the N evolution, or the N flow. This is a symmetry, and this is what we call a global gauge symmetry. Global here means just, look, it's a symmetry. Something is preserved. Something that the Hamiltonian is preserved when you move in the direction of the n vector, right? But because what is preserved along this flow is you flow by changing the momenta, but you change them by a constant, independent of I. That's what global means. If these were positions, if the I were positions of a particle, then the flow would be that you change the phase of the wave function all by the same constant factor independent of position. That's what that means. But we do not know that yet. Um, that, that's for later. So, so very good. So what we want to say here, what is the gauge symmetry? The gauge symmetry is that, so this is the symmetry. If the curve theta as a function of tau and pi as a function of tau is a solution of the Hamilton's equations, if you have a particular curve that gives the flow according to Hamilton's equations, then the curve theta pi prime and theta prime and pi prime are also going to be a solution of Hamilton's equations, provided the theta matches and the pi matches up to a constant nu, right? Which is exactly what we had there. So if this curve is a solution, then this curve is a solution too. That's exactly what we mean by a symmetry. If the planet goes around the sun in a particular ellipse, rotation invariance means that there is another ellipse that does the same thing when you just rotate, right? Well, here it's if you find one solution of the Hamilton's equations, then there is another solution in which you just displace the momentum by a constant. Very good. The proof of this is fairly automatic. All you have to say is, look, if you have the Hamiltonian function and you evaluate at the new points, well, this is going to be, by definition of what the new points are, just displace the momentum. But the fact that H is independent of nu means that here I can write any value of nu I want, including 0. So that's what it means. The Hamiltonian is exactly the same whether you write it with primes or without primes. And so now we can do figure out what the new trajectories are. The new trajectories are going to be given by something like that, but the thetas are the same because that's what the thetas, when you change nu, that's what, nothing happens. And this guy here is given by Hamilton's equations. And this is as a function of theta pi. But this guy here, as we just shown, is the old Hamiltonian. Let me write it in the next line. This is the Hamiltonian written in terms of the pi primes. This equals that. But now we have to do the derivative with respect to pi, and this guy has pi prime. So the way we're gonna do it is we got the derivative with respect to pi prime, and then the derivative of pi prime with respect to pi. But this guy here, because this guy here is just a constant, that is just a constant, the derivative with respect to pi prime is equal to 1, which means this is just the h theta prime pi prime with respect to pi I prime. So you can see that whatever, if the old thetas satisfied equation of motion, the flow with the old thetas, the new trajectory with theta primes also satisfies the equation of motion. And you can do exactly the same calculation for the pi primes. And this is, by definition of the pi prime, it's just shifting by a constant nu. So when we take the derivative with respect to tau, nothing, it vanishes. And this is minus the h theta prime d theta I, and this we write as d theta I theta prime pi prime, and but we want to do the derivative with respect to theta prime. Theta I and theta prime I are the same, so we just put the primes there and we are done. So that concludes the proof. So how do we read all of these things? So here is the interpretation. The idea here is that the constraint, when we impose normalization, reduces the number of degrees of freedom by 1. So this is what brings us to the simplex. We want a description that in which probabilities evolve along the normalized surface. So the constraint reduces the degree of freedom by 1. So the question then that arises is, okay, you got rid of one of the coordinates, what happens to the momenta? Okay, the condition that happens here is that the symmetry that we have just uncovered, which is basically you go from pi to pi plus any constant, eliminates another degree of freedom of the momentum. And the reason it eliminates them is that while these degrees of freedom of all the momenta are still there, we recognize that any shift by a constant does not lead to a new state. It gives exactly the same state that you had before. So the symmetry of shifting by a constant eliminates a momentum degree of freedom by making them equivalent. What you make equivalent are the states in which this and that different momenta, you're making them equivalent. It's not a different state. So you don't eliminate them in the sense of getting rid of them. You eliminate them in terms of saying they're physically equivalent. Very good. So maybe I can try. So this is what we call a gauge symmetry, right? So we eliminate an extra coordinate by imposing a constraint, and an extra probability, an extra coordinate on the base manifold, and we eliminate the other by declaring them the momenta and the difference between two states that differ by a constant in momentum. We declare that unphysical. There is no physics to it. So this is the gauge symmetry. Now, when you have a gauge symmetry like this, states in which you do not change the probability, but you do change the momenta by a constant, you have flows, right? These flows, the flow of equivalent states generated by the constraint or by the vector n, both languages are allowed. The flow of equivalent states generated by n is called an orbit, a gauge orbit. And so now what we would like to study is the following. If you have a vector field, if you have a certain curve, and let's call the curve x as a function of generic. Let me see. Let's call the parameter mu. So it could be tau, but it can be anything. Suppose you have a curve in the space. Clearly there is a tangent vector there, dx d mu. But now, if you can actually displace in the direction of n, you can displace this curve, displace any point, you can displace it by a nu, and by a constant, and put parameter nu. And here you can displace it by a constant, parameter nu, and then by a constant. But these constants, any flow in the direction of nu is allowed. It will give you an equivalent state. So the question is that this constant here may itself depend on the value of nu. And so now we have a different curve in which at each point you move to an equivalent state that is independent. The change is independent of the I, but it need not be independent of where you are along the curve. So now the question here is, I have a different vector. And so the point of all of this is that if we have a vector dd mu, then we can construct we have an equivalent vector v prime, and the point of this v prime is that these are all allowed states, and these are all equivalent states given by a flow along n. So these guys, how are the vectors here related to each other? And the connection between the two is that except for a constant, these vectors are going to differ by a component along the direction of n. So how does this work here? So as an example, n is equivalent to n prime equals n plus some constant n. Here's another one. If you have the vector h, then the vector h prime at the points theta prime, phi prime is going to be equivalent to the vector h at the points h theta pi with some constant, and in this case the constant is going to be d nu d tau n. So let's see how that comes about. Well, the idea is that if you have a curve, theta alpha I as a function of mu, then this is just, well, this is the curve. Let me write it like in the form of a curve. The points are going to be certain functions of the parameter nu. And so what this means is that theta I as a function of mu goes to the same thing, and pi I as a function of mu goes to pi I mu plus nu, where now mu nu can be a function. So we're just doing this displacement, but the displacement can be a little bit in some places, a lot in some others, but always independent of the I. So now if we're going to figure out the vector theta I d mu d pi I d mu goes into this nu vector in which the theta components do not change, but the pi components change by a quantity that is constant, not in the sense that it is independent of mu, the point on the trajectory, but it is independent of I. So this is the statement that these vectors here are equivalent because they are tangent to equivalent curves. Very good. What do we want to say now here? Yes, to finish this, once you have a bunch of vectors that are equivalent to each other in the sense that they differ by a certain amount, but represent vectors that are tangent to equivalent curves. You have a family of these guys. Very good. Once you have a family of points in a gauge orbit and they're all equivalent, you might say, I'm going to pick one as being the representative. Given a family of equivalent points, like up here, like here, or of equivalent vectors. So once you have a class of equivalent anything, it is convenient to choose a representative. You would talk about the whole family by just talking about one of them. It is convenient to choose a representative. This is called fixing the gauge. In the particular case that we are dealing here, it is convenient to fix the gauge by specifying that whatever these vectors here are, these vectors here, these are just the theta, the mu. Whatever these vectors are, we're going to say that if we sum over all of them, in this case, we get 0 by establishing the constraint. You move along the constraint, tangent to the simplex. And it is convenient to say that for the other, I'm sorry, this is I, this is I. We sum over all the i's, and here the condition that is useful is to say that you take the expected value of these guys here. It's not clear at this point why this is convenient. You're going to see later that this is indeed so. And so we fix the gauge by imposing these conditions. Enough for now. Next, we're going to come back and make further advances into figuring out the desired Hamiltonian functions that we need to do physics. See you then.